Stellar black holes. Stellar black holes form when the most massive stars in the universe reach the end of their lives and collapse under their own gravity. These cosmic monsters represent the first and most common type of black hole, created through one of the most violent processes in nature. When a star at least 20 times heavier than our Sun exhausts its nuclear fuel, it can no longer maintain the outward pressure needed to counteract its own gravitational pull. The star's core caves in on itself in a catastrophic event called gravitational collapse. This process happens incredibly quickly, with the core shrinking from thousands of kilometers across to just a few dozen kilometers in less than a second. During this collapse, gravity overwhelms every other fundamental force in the universe. The electromagnetic force that keeps atoms intact, the strong nuclear force that binds protons and neutrons together, and the weak nuclear force all become powerless against the crushing weight of gravity. Matter gets compressed to densities so extreme that a teaspoon of this material would weigh as much as Mount Everest. The result is an object that weighs between 3 and 100 times the mass of our Sun, yet fits into a sphere no larger than a typical city. To understand this scale, imagine compressing the entire mass of dozens of suns into an area smaller than Manhattan. The gravitational field becomes so intense that it warps the fabric of space-time itself, creating a region where the normal rules of physics break down. Around every stellar black hole exists an invisible boundary called the event horizon. This represents the point of no return, where the gravitational pull becomes so strong that nothing, not even light traveling at 300 million meters per second, can escape. The size of this boundary depends on the black hole's mass. A black hole with 10 times the mass of the Sun would have an event horizon roughly 30 kilometers across. Despite being invisible by definition, astronomers can detect stellar black holes through their gravitational effects on nearby objects. When a stellar black hole exists in a binary system with a normal star, it can steal gas and material from its companion. This stolen matter doesn't fall straight into the black hole. Instead, it forms a swirling disk called an accretion disk, where friction heats the material to millions of degrees. This superheated gas glows brilliantly in X-rays, creating a beacon that telescopes can detect from thousands of light years away. Scientists estimate that our galaxy alone contains millions of stellar black holes, most drifting silently through space without any nearby stars to feed on. These dormant black holes remain completely invisible unless they happen to pass in front of a distant star, causing the star's light to bend and brighten in an effect called gravitational microlensing. The discovery of gravitational waves by the LIGO and Virgo detectors has opened a new window into stellar black holes. When two stellar black holes spiral into each other and merge, they create ripples in space-time that travel across the universe at the speed of light. Intermediate black holes. Intermediate black holes represent one of the most puzzling mysteries in modern astrophysics. These objects occupy the middle ground between stellar black holes and supermassive black holes, weighing anywhere from a few hundred to roughly 100,000 times the mass of our Sun. Despite decades of searching, they remain some of the most elusive objects in the universe. The mystery of intermediate black holes lies not just in their rarity, but in what their existence could reveal about how black holes grow and evolve. Stellar black holes form from collapsing stars and typically weigh no more than a few dozen solar masses. Supermassive black holes, found at the centers of galaxies, can weigh millions or billions of times more than our Sun. The gap between these two categories seems too large to bridge through normal growth processes. If a stellar black hole tried to grow into a supermassive black hole by consuming nearby matter, it would take far longer than the current age of the universe. Yet, observations show that supermassive black holes already existed when the universe was less than 1 billion years old. Intermediate black holes could provide the missing link, serving as the seeds that allowed supermassive black holes to grow so quickly in the early universe. Finding intermediate black holes proves incredibly difficult because they lack the obvious signatures of their larger and smaller cousins. Unlike supermassive black holes, which often power brilliant quasars that can be seen across billions of light years, intermediate black holes are typically quiet and dim. They don't consume vast amounts of matter, so they don't produce the dramatic light shows that make supermassive black holes easy to spot. Scientists search for intermediate black holes by looking for their gravitational effects on surrounding stars and gas. In dense star clusters, where hundreds of thousands of stars are packed into a relatively small region, an intermediate black hole at the center would influence the motions of nearby stars. By carefully mapping the orbits of these stars, astronomers can infer the presence of a massive, invisible object. One promising hunting ground is globular clusters, ancient collections of stars that orbit around galaxies. Some globular clusters show evidence of central mass concentrations that could be intermediate black holes. The globular cluster 47 Tucanae, for example, contains something with several thousand solar masses at its center, based on the way stars move in the cluster's core. Dwarf galaxies also provide potential homes for intermediate black holes. These small galaxies, which contain only a fraction of the stars found in larger galaxies like the Milky Way, sometimes show signs of central black holes that are neither stellar nor supermassive in size. The galaxy HLX-1, located about 290 million light-years from Earth, appears to host a black hole weighing roughly 20,000 solar masses. Occasionally, intermediate black holes reveal themselves through violent events. When such a black hole tears apart and consumes a passing star, the resulting burst of X-rays can be detected by space-based telescopes. These tidal disruption events provide some of the strongest evidence for intermediate black holes, though they occur rarely and unpredictably. Supermassive black holes. Supermassive black holes represent the true giants of the cosmic hierarchy, containing masses that range from millions to billions of times that of our Sun. These titanic objects don't lurk in random corners of space like their smaller stellar cousins. Instead, they occupy positions of supreme importance at the hearts of galaxies, where they serve as invisible anchors that help shape and control the evolution of entire galactic systems. The supermassive black hole at the center of our own Milky Way galaxy, known as Sagittarius A star, contains approximately 4 million solar masses, compressed into a region smaller than the orbit of Mercury. Despite being 26,000 light-years away from Earth, its gravitational influence is so powerful that astronomers can observe individual stars whipping around it at incredible speeds. Some of these stars complete full orbits in just 16 years, reaching velocities of up to 5,000 kilometers per second at their closest approach. The scale of supermassive black holes defies easy comprehension. While stellar black holes might be compared to cities in size, supermassive black holes can be larger than our entire solar system. The supermassive black hole in the galaxy Messier 87 contains more than 6 billion solar masses. In 2019, this monster became the first black hole ever directly imaged by the Event Horizon Telescope, appearing as a glowing ring of superheated gas surrounding a dark central shadow. The formation of supermassive black holes presents one of the greatest puzzles in modern astrophysics. No single star could ever grow large enough to collapse into an object containing millions of solar masses. Several competing theories attempt to explain their origins. One possibility suggests they began as smaller black holes that grew over billions of years by consuming stars, gas, and other black holes. Another theory proposes that in the early universe, massive clouds of primordial gas collapsed directly into supermassive black holes without ever forming stars. The mystery deepens when considering how quickly these giants must have grown. Observations reveal supermassive black holes already existed when the universe was less than 1 billion years old, leaving insufficient time for gradual growth from stellar mass seeds. This timeline problem has led some scientists to propose that supermassive black holes formed from intermediate mass black holes or through other exotic mechanisms in the early cosmos. Supermassive black holes don't simply sit passively at galactic centers. They actively influence their surroundings through a process called accretion. As matter spirals toward the black hole, gravitational forces compress and heat it to temperatures exceeding millions of degrees. This superheated material forms an accretion disk that glows brilliantly across the electromagnetic spectrum. The energy released during accretion can outshine the combined light of all stars in the host galaxy. When supermassive black holes feed actively, they become visible as quasars, among the most luminous objects in the universe. These cosmic beacons can be detected from billions of light-years away, serving as lighthouses that illuminate the early universe. The energy output from an actively feeding supermassive black hole can drive powerful winds that blow gas out of the galaxy, regulating star formation and sculpting galactic evolution over cosmic time. Every large galaxy observed appears to contain a supermassive black hole at its center, suggesting a fundamental connection between black hole growth and galaxy formation. Primordial black holes. Primordial black holes represent a completely different category of cosmic objects that may have formed not from collapsing stars, but during the first moments after the Big Bang itself. Unlike stellar or supermassive black holes, which require millions or billions of years to develop, primordial black holes could have emerged when the universe was less than 1 second old, making them potentially the oldest structures in existence. In the earliest moments of cosmic history, the universe existed in a state of extreme density and temperature that defies normal comprehension. During this primordial epoch, tiny fluctuations in the fabric of space-time itself could have concentrated matter so intensely that gravity immediately crushed it into black holes. These density variations, possibly quantum in nature, would have created pockets where matter became compressed beyond any threshold that normal physics could resist. The theoretical size range of primordial black holes spans an almost incomprehensible spectrum. Some could be smaller than individual atoms, yet contain masses measured in kilograms or tons. Others might rival asteroids or even mountains in weight while occupying spaces no larger than grains of sand. To visualize this extreme compression, imagine squeezing the entire mass of Mount Everest into a region smaller than a proton, creating an object with gravitational effects far exceeding anything found in normal matter. Scientists have become intensely interested in primordial black holes because they could potentially solve one of cosmology's greatest mysteries: the nature of dark matter. Astronomical observations consistently show that galaxies rotate and move in ways that cannot be explained by the visible matter they contain. Something invisible must be providing the additional gravitational pull needed to hold galactic structures together. But decades of searching have failed to identify what this dark matter actually is. If primordial black holes exist in sufficient numbers, they could account for some or all of the missing dark matter in the universe. Unlike exotic particles that interact only weakly with normal matter, primordial black holes would be purely gravitational objects, invisible, simply because they emit no light rather than because they belong to some unknown category of particle physics. The implications extend far beyond dark matter. Primordial black holes could also explain how supermassive black holes grew so large so quickly in the early universe. Instead of starting from stellar mass seeds that would take too long to reach billions of solar masses, supermassive black holes could have begun as much more massive primordial seeds, giving them a significant head start in their growth process. Detecting primordial black holes presents enormous challenges because of their potentially tiny sizes and lack of nearby matter to consume. Scientists search for them through several indirect methods. Gravitational microlensing occurs when a primordial black hole passes between Earth and a distant star, causing the star's light to brighten temporarily as the black hole's gravity acts like a cosmic magnifying glass. Another detection method involves looking for the effects of Hawking radiation. According to theoretical physics, all black holes slowly evaporate by emitting particles, with smaller black holes evaporating faster than larger ones. Primordial black holes with masses similar to asteroids would be completing their evaporation process right now, potentially creating detectable bursts of high-energy particles and radiation. Quantum black holes. Quantum black holes exist at the intersection of two fundamental theories that normally operate in completely separate realms of physics. Einstein's general relativity governs the behavior of massive objects and the curvature of space-time on cosmic scales, while quantum mechanics describes the probabilistic and uncertain world of subatomic particles. When these two frameworks collide at the smallest possible scales, they produce the theoretical concept of quantum black holes. These hypothetical objects would exist at what physicists call the Planck scale, named after physicist Max Planck, who first identified the fundamental limits of measurement in nature. The Planck length measures approximately 10 to the negative 35th meters, a distance so small that it makes atoms appear gigantic by comparison. A hydrogen atom is roughly 10 trillion times larger than the Planck length, illustrating just how incredibly tiny this scale truly is. At the Planck scale, the normal concepts of space and time begin to break down. The smooth fabric of space-time that Einstein described becomes a seething foam of quantum fluctuations, where virtual particles constantly pop into existence and annihilate each other in time frames shorter than any possible measurement. In this quantum realm, a black hole would represent the ultimate meeting point between gravity and quantum uncertainty. A quantum black hole would contain a mass compressed into a region at or near the Planck length. Despite being unimaginably small, such an object would still possess the fundamental properties that define all black holes: an event horizon beyond which nothing can escape, and a central singularity where density becomes infinite. However, quantum effects would dominate the behavior of such tiny black holes in ways that larger black holes never experience. The most significant quantum effect affecting these microscopic black holes is Hawking radiation, named after physicist Stephen Hawking, who first described the phenomenon. According to quantum field theory, the intense gravitational field near a black hole's event horizon causes pairs of virtual particles to separate, with one particle falling into the black hole while the other escapes as real radiation. This process causes all black holes to slowly evaporate over time. For stellar and supermassive black holes, Hawking radiation occurs so slowly that these objects would take longer than the current age of the universe to evaporate completely. A black hole with the mass of our Sun would require 10 to the 67th years to disappear entirely. However, quantum black holes would evaporate almost instantaneously, releasing their entire mass energy in a brilliant flash lasting only 10 to the negative 43rd seconds. Some theoretical physicists speculate that quantum black holes might have formed during the extremely high energy conditions present immediately after the Big Bang. Others wonder whether modern particle accelerators like the Large Hadron Collider could create them during high-energy collisions between protons. However, even if such creation were possible, the resulting quantum black holes would vanish so quickly that detecting them would prove nearly impossible with current technology. The study of quantum black holes serves a purpose beyond mere theoretical curiosity. These objects represent a crucial testing ground for theories that attempt to unify general relativity with quantum mechanics into a single framework called quantum gravity. Rogue black holes. Rogue black holes represent one of the most terrifying possibilities in the cosmos. Invisible gravitational monsters drifting through space without any fixed location or predictable orbit. Unlike supermassive black holes that remain anchored at galactic centers or stellar black holes that stay roughly where their parent stars died, rogue black holes wander freely through the universe, making them nearly impossible to detect until they interact with nearby matter or pass close to other objects. These cosmic wanderers form through several violent processes that can eject black holes from their original locations. When massive stars explode in asymmetric supernovae, the uneven distribution of energy can kick the resulting black hole away from its birthplace at speeds reaching hundreds of kilometers per second. Binary black hole systems can also create rogues when gravitational interactions with a third black hole eject one member of the pair, sending it careening through space at tremendous velocity. Galactic collisions provide another mechanism for creating rogue black holes. When two galaxies merge, their central supermassive black holes eventually spiral toward each other in a cosmic dance that can last millions of years. If a third supermassive black hole enters this system, the complex gravitational interactions can slingshot one of the black holes completely out of the merged galaxy, creating a rogue supermassive black hole wandering through intergalactic space. The most frightening aspect of rogue black holes lies in their stealth. Since black holes emit no light of their own, a rogue black hole approaching our solar system would remain completely invisible until its gravitational effects became apparent. By that time, the disruption to planetary orbits and the structure of the solar system could already be underway. Even a stellar mass rogue black hole passing through the outer regions of our solar system could destabilize the orbits of planets and send comets from the Oort cloud cascading toward the inner solar system. Scientists estimate that millions of rogue black holes may be drifting through the Milky Way galaxy at any given time. Most of these would be stellar mass black holes ejected from their birth sites by supernova kicks, but some could be intermediate mass or even supermassive rogues expelled from other galaxies during cosmic collisions. The vast majority remain completely undetected, invisible ghosts moving through the darkness between stars. Detecting rogue black holes requires indirect methods that rely on their gravitational effects rather than any light they might emit. Gravitational microlensing provides the most promising detection technique. When a rogue black hole passes between Earth and a distant star, its gravity acts like a cosmic magnifying glass, temporarily brightening the background star in a characteristic pattern that reveals the presence of the intervening black hole. In 2022, astronomers announced the first confirmed detection of a rogue black hole using this microlensing technique. Located approximately 5,000 light-years from Earth, this stellar mass black hole revealed itself by distorting the light from a more distant star over several months. The discovery confirmed that rogue black holes do indeed exist and wander through our galaxy, though determining their exact numbers and trajectories remains extremely challenging. The unpredictable nature of rogue black holes makes them particularly unsettling. Unlike other cosmic threats that follow predictable orbits or remain in known locations, rogues could appear anywhere at any time. Magnetars. Magnetars represent the most magnetically powerful objects known to exist in the universe, possessing magnetic fields so intense they fundamentally alter the behavior of matter and energy in their vicinity. These exotic stellar remnants form when the most massive stars undergo core collapse during supernova explosions. But unlike typical neutron stars, magnetars develop magnetic fields that are quadrillions of times stronger than Earth's protective magnetic field. The formation process of magnetars begins similarly to other neutron stars, with a massive star exhausting its nuclear fuel and collapsing under its own gravity. However, magnetars likely form from stars that were rotating extremely rapidly before their collapse, or from binary systems where complex interactions amplify the magnetic field during the collapse process. The exact mechanism remains partially mysterious, but the result is a neutron star with a magnetic field measuring between 10 to the 14th and 10 to the 15th Gauss. To understand the incredible strength of these magnetic fields, consider that Earth's magnetic field measures roughly half a Gauss, while the strongest magnetic fields created in laboratories reach about 45 Tesla, or 450,000 Gauss. A magnetar's field is so powerful that it could erase the magnetic strip on a credit card from a distance of 100,000 kilometers and would be lethal to human life from a distance of 1,000 kilometers due to the disruption of biological processes. The intense magnetic field of a magnetar affects the very structure of atoms in its vicinity. In the strongest regions near the magnetar's surface, the magnetic field becomes so powerful that it stretches hydrogen atoms into elongated shapes, with the electron orbits becoming highly distorted. This creates exotic forms of matter that cannot exist anywhere else in the universe, where the normal rules of atomic physics break down under the influence of extreme magnetism. Magnetars announce their presence through sudden, violent outbursts of high-energy radiation. These starquakes occur when the magnetar's crust, made of crystallized nuclear matter, cracks under the enormous stress created by the twisting magnetic field lines. When the crust fractures, it releases energy equivalent to all the earthquakes on Earth over several million years, but concentrated into a burst lasting only a few seconds. The most powerful magnetar flare ever recorded occurred in December 2004, when magnetar SGR 1806-20 unleashed a burst of gamma rays and X-rays so intense that it temporarily blinded satellites throughout the solar system and caused measurable changes in Earth's upper atmosphere. This flare, originating from a magnetar located 50,000 light-years away, released more energy in 1/10 of a second than our Sun produces in 100,000 years. The magnetic field lines of magnetars extend far beyond the neutron star itself, creating a magnetosphere that can stretch for thousands of kilometers. Within this region, charged particles become trapped and accelerated to nearly the speed of light, creating beams of radiation that sweep across space like cosmic lighthouses. When these beams point toward Earth, we detect them as regular pulses of radio waves, X-rays, or gamma rays. Only about 30 magnetars have been confirmed to exist in our galaxy, making them among the rarest types of stellar objects. Their extreme magnetic fields gradually decay over time, with most magnetars remaining active for only about 10,000 years before their magnetic fields weaken sufficiently that they resemble ordinary neutron stars. Ton 618. Ton 618 stands as one of the most terrifying and incomprehensibly massive objects ever discovered in the universe, representing the extreme upper limit of what black holes can become. This hyperluminous quasar, located 10.4 billion light-years from Earth, harbors a supermassive black hole so enormous that it challenges our understanding of how such monsters could have formed and grown to such incredible proportions in the relatively young universe. The supermassive black hole at the heart of TON 618 contains an estimated 66 billion solar masses, making it one of the most massive black holes ever measured. To grasp the scale of this cosmic leviathan, consider that it weighs roughly 16,000 times more than Sagittarius A star, the supermassive black hole at the center of our own Milky Way galaxy. If this monster were placed at the center of our solar system, its event horizon would extend well beyond the orbit of Neptune, encompassing our entire planetary system within its point of no return. The discovery of TON 618 began in the 1950s during astronomical surveys designed to catalog blue stellar objects in the night sky. Initially classified as a faint blue star, its true nature remained hidden for decades, until advancing technology revealed that this seemingly ordinary point of light was actually one of the most luminous objects in the observable universe, shining with a brightness of 140 trillion suns. The immense luminosity of TON 618 comes from the violent process of accretion, where matter spirals into the central black hole at an extraordinary rate. As gas, dust, and even entire stars fall toward the event horizon, gravitational forces compress and heat this material to temperatures exceeding millions of degrees. The resulting accretion disk glows with such intensity that it outshines the combined light of hundreds of billions of stars, creating a beacon visible across most of the observable universe. What makes TON 618 particularly unsettling is not just its current size, but the implications of its existence in the early universe. The light we observe from this quasar left its source when the universe was only 3.7 billion years old, less than one-third of its current age. This means that somehow, in the relatively brief cosmic time since the Big Bang, this black hole managed to accumulate a mass equivalent to 66 billion suns. The rapid growth required to reach such enormous proportions presents a significant challenge to current theories of black hole formation and evolution. Even if TON 618 began as a supermassive seed weighing thousands of solar masses, it would need to consume matter at an almost impossible rate to reach its current size so quickly. The black hole would need to feed continuously at or near the theoretical maximum rate, known as the Eddington limit, for billions of years without interruption. The environment around TON 618 must be utterly hostile to any form of life as we understand it. The intense radiation from the accretion disk would sterilize planets across thousands of light years, while the gravitational effects would disrupt the formation of stable solar systems throughout the surrounding region. Jets of high-energy particles, accelerated to nearly the speed of light, stream away from the black hole's poles, creating death rays that extend across millions of light-years of space. The existence of TON 618 forces astronomers to confront the possibility that the early universe contained mechanisms for creating and feeding black holes that no longer operate today. The event horizon. The event horizon represents the most terrifying boundary in the universe, an invisible sphere surrounding every black hole that marks the absolute point of no return. This cosmic threshold exists not as a physical surface that could be touched or observed directly, but as a mathematical boundary in space-time itself, beyond which the fundamental nature of reality breaks down, and the normal rules of physics cease to apply in ways that human minds can comprehend. The concept of the event horizon emerged from Carl Schwarzschild's solution to Einstein's field equations, developed in 1916 while Schwarzschild served as a soldier on the Russian front during World War I. Working in trenches between battles, he calculated the geometry of space-time around a massive, non-rotating object and discovered that at a specific distance from the center, something extraordinary happens to the fabric of space and time itself. The size of an event horizon depends entirely on the mass of the black hole it surrounds. For a black hole with the mass of our Sun, the event horizon would have a radius of approximately 3 kilometers, double the mass, and the radius doubles as well. This relationship, known as the Schwarzschild radius, means that supermassive black holes possess event horizons that can stretch across distances larger than entire planetary systems, while stellar mass black holes have horizons measured in mere kilometers. What makes the event horizon so fundamentally terrifying is the complete breakdown of causality that occurs at this boundary. In normal space-time, cause precedes effect, and information can travel from one location to another. However, at the event horizon, the curvature of space-time becomes so extreme that all possible paths lead inexorably inward toward the central singularity. Even light, traveling at the maximum possible speed in the universe, cannot escape once it crosses this threshold. From the perspective of an outside observer, the event horizon creates one of the most disturbing phenomena in physics: time dilation taken to its absolute extreme. As an object approaches the event horizon, time appears to slow down dramatically due to the intense gravitational field. To someone watching from a safe distance, a person falling toward a black hole would appear to slow down and freeze at the event horizon, their image becoming redder and dimmer until it fades from view entirely. However, from the perspective of the falling observer, the experience would be entirely different and far more horrifying. They would pass through the event horizon in what seems like normal time, completely unaware that they had crossed the point of no return. The gravitational field would continue to strengthen as they fell inward, stretching their body vertically and compressing it horizontally in a process that physicists have grimly nicknamed spaghettification. The event horizon also represents a fundamental limit to human knowledge and observation. No information can ever escape from beyond this boundary, meaning that whatever happens inside a black hole remains forever hidden from the outside universe. This creates what physicists call the information paradox, a conflict between general relativity and quantum mechanics regarding whether information that falls into a black hole is destroyed or somehow preserved. In 2019, the Event Horizon Telescope collaboration achieved the remarkable feat of imaging the shadow cast by the event horizon of the supermassive black hole in galaxy Messier 87, providing humanity's first direct visual evidence of this cosmic boundary.